Welcome to Puzzles to Exercise the Mind, lesson number 9. Our first puzzle in this lesson comes from the very first SAT test in 1926. I have a reference here at the bottom to the test itself. There were many categories, unlike the more recent SAT test. One of the categories was called sequences, or some similar name, and there were a series of sequence questions which got harder and harder, and this was the last one in the list, so this was the hardest one. Maybe just to get you in the mood for doing sequence problems, I have a simple one up here, 1, 4, 7, 10, and so one of the procedures is normally to take the difference. You can see here that's 3, 3, 3. So if we just add 3 again, we get 13. So that was pretty easy. This one here, as I say, is not it's not obvious at all. The approach, or one of the approaches, is you could take differences. You could take, you could usually divide one into the other. That doesn't look like it'll work here, but sometimes you have multiplication rather than addition is the progression in the series. Now this one's a little bit harder because you're going up and down, the values are not going in one direction, so there's some type of alternating pattern here. The other thing I want to mention is that the questions, there are a lot of questions in this first exam, and it averaged only less than 30 seconds for each one, and if you wanted to go over all the, try to answer all the questions. So something like this would probably take most people longer than 30 seconds, but some of the easier ones could be done pretty fast, and then that would leave a little bit of extra time to work on something like this, maybe a few minutes. And keep in mind that in 1926 there were no calculators, so people in general were better at doing calculations by hand, so that would have been helpful in terms of solving this. And the other thing is, it appears that the sections of the SAT were known in advance, and one section was basically dedicated to sequences. So I guess the students could have studied how to solve different sequences before they actually took the exam. So we have the answer here on this slide for our sequence problem. So if we take the difference as we move along here, so if we take 21 minus 750, we get minus 729, and then 264 minus 21, we get 243. Then 183 minus 264, we get minus 81, and then 210 minus 183, and we get 27. We don't know what these last two are yet, so we'll get to that in a second. So that was the one thing to do. Now, even after you've done these subtractions, you may not see the pattern. It took me a little bit to see it, but this kind of gives it away a little bit. This is 3 cubed, and then this is minus 3 to the 4th. Then once you see the pattern here, you figure, well, maybe this is another power of 3, and of course it is. It's 3 to the 5th, and this is minus 3 to the 6th. So then the difference between these two you would expect to be a minus and 3 squared. That's minus 9. And then you would go positive, but then it would just be 3 to the 1 power of 3. And you would go up one to up in value to 204. So these are the next two values in the sequence. I have a few more sequence problems for you to try. First one is this sequence here. You notice it's going down, 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 so this is a decreasing sequence. Then we have an increasing sequence. And then the third one is not easy. I'll warn you that that's a different pattern from what you might be expecting. So you may want to pause the video here, and I'll come back on this same slide and explain the solutions. Okay, I'm back. So the first one is you're going down by 2, then down by 3, then down by 4, down by 5, and then you go down by 6. So it would be 6 from 16 or 10. So that wasn't too bad. The next one are cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed. So 5 cubed. It's 125. Next one is tricky. So the pattern is the nth term, and you're starting from the 0th term here, by the way. So the nth term equals the term before it plus n squared. So we're looking for the 5th term here, 0, 1, 2, 3, 4, 5. So the 5th term is the term before it, 30, plus n, which is our 5 here, squared. And you get 30 plus 25 is 55. You may want to just verify that it works for some of the ones you already know. For example, let's say we didn't know 30 yet. So then the 4th term would be 14 plus 4 squared, which is 16. 14 and 16 is 30. So you can check it for the other ones. I mean, these can get very complicated once you start putting in squares and recurring off of the previous terms in addition to something like this. And I have no doubt that you could figure out another valid pattern that would fit these numbers here. So as you start getting very tricky with the patterns, and especially if you don't give like a lot of numbers in the pattern, you would leave open the possibility that there's more than one solution. So in fact, if you find a different pattern that fits this, put it in the comments. That would be of interest. Okay, so there's plenty of these on the internet if you're looking for pattern sequence problems, and it's a good test. You can see here we have several different approaches or different patterns. We can have just the subtraction or addition, then we can have multiplication or division, and then we have these more complex patterns like the one we saw here. This problem is one of a class of problems. They're known as work problems. They're from high school algebra. They're among the more difficult ones, especially if you haven't seen one. To try to place the words in terms of an equation is a bit difficult, but let's have a look at it. Xavier can mow a lawn, a given lawn, in 6 hours. Eves can mow the same lawn in 5 hours, and Zachary can mow the same lawn in 3 hours. If all three work together and don't interfere with each other, how long will it take to mow the given lawn? So just in terms of assumptions, when I say the same lawn, I mean with the same length of grass. So obviously if one just mowed the lawn, then the next one's going to be able to do it pretty quickly or not do any work at all. But the idea is given a certain length or growth of the grass, these are the numbers that each person can do. And you notice I made them X, Y, and Z just to kind of set you up for the equation that we're going to need to solve this. So have a think about this, and then I'll give you the solution. So the trick is to write down this information we were given in terms of rates. You can see here X, use the pointer, X, or Xavier, I'll just call him X. X can mow the lawn at a rate of 1 lawn per 6 hours, and then the other two, Y and Z, can mow the lawn at 1 lawn per 5 hours and 1 lawn per 3 hours. So we could just add these rates together to get their combined rate. We get a common denominator. We get 21 over 30, but we want the rate in terms of lawns per hour. So it'll be 1 lawn per 30 over 21 hours. And we can convert that to 10 over 7. Or should I say reduce it to 10 over 7. So that would come to 1.43 hours. And then we can multiply 0.43 times 60 minutes, and we would get 1 hour and about 25.8 minutes. So that's the general technique. And you can do it with other things, like you could say the 3 people or 4 people, whatever the number is, they can dig a ditch in certain number of hours or a number of minutes, and how long would it take them to dig that ditch in the ground. if they work together without interfering. So you could talk about digging, you could mowing lawn, painting a house. If they can paint a room in a house and at a rate of the one room per 2 hours, and somebody can do it in 3 hours and so forth, that would be another rate problem. So we'll have a variation of this on the next slide, which is a bit easier once you know the answer to this puzzle. We have a variation on the previous puzzle. Let's assume we're using the same lawn again as sort of our test case or measurement stick in terms of how quickly people can mow lawns. So let's say Xavier has left the team, and now Eves and Zachary are left with looking for another person, and they would like to go down from that 1 hour and 25 or so minutes down to just an hour with that third person at it that they need to find. So how fast would the new person need to be able to mow that given lawn alone in order for the three of them to collectively be able to mow that same lawn in just an hour? So the approach in solving this variation of the original lawn problem is very similar to what we've done in for the first problem. We have the additional person. We'll call that person X, and he or she has this rate one lawn per X hours. So we don't know what that is, but we can use the same equation here. We have the rate of the new person, and we know the rates of the other two, Y and Z. It's one lawn per 5 hours, one lawn per 3 hours, and we want the sum of these rates to equal 1, because we want the three of them to be able to mow that lawn, that test case lawn in 1 hour. So once you have this, it's pretty easy. It's just a matter of subtracting 1/5 and 1/3 from 1. We get 1 over x equals 7 over 15, or in other words, x equals 15 over 17. And if we convert that to a mixed fraction here, 2 1/7, and then we can convert that to 2 hours, 8 minutes, 34 seconds. So this new person will need to be able to mow the lawn, the given lawn, in 2 hours, 8 minutes, 34 seconds in order for all three of them working together to be able to mow the given lawn in 1 hour. We have one more variation of the lawn mowing problem. In this version, we're not actually given specific numbers. We're just given relative rates amongst the three people mowing the lawn. So we're given that Eves can mow the given lawn twice as fast as Zachary, and Xavier can mow the given lawn 3 times as fast as Zachary. So we're given everything in terms of how fast Zachary can mow the lawn. What can we say about the rate at which all three can mow the given lawn together? So you may want to pause here because I'm going to give you the answer on the same slide. When I come back, I'll do that. Okay, so here's the solution. We let Zachary's rate be 1 lawn per Z hours. We don't know what the Z is, but so we'll put a variable here. Then Eve's rate is 1 lawn per 1/2 hour, because Eves can mow the given lawn twice as fast as Zachary. So if Zachary takes Z hours, then Eves would take 1/2 Z hours to mow the lawn. And then since Xavier can mow the lawn 3 times as fast as Zachary, his rate would be 1 lawn per 1/3 Z hours. And then our task is just to figure out how fast the three of them can do that together. So we add the 3 rates. This is the rate of, I'll use the pointer here. This one here is the rate of Xavier. So he's the fastest. And then the second one here is the rate of Eves. And then Zachary's rate is 1 over Z. Then you can just flip these to the top. The 1/3 is 3, 2, 1. And you add those together, you have a common denominator of Z. So 1 plus 2 plus 3 is 6. Then you convert it back to the rate of lawns per hour. So 1 lawn per 1/6 z hours. So if z happened to be 6 hours, for example, then their collective rate would be 1/6 times 6. So it would be 1 hour in that case. So there's a lot of different games you could play with this type of puzzle where you're given different bits of information, but the equation is very similar, and you could do it for we've shown it here for 3 people, but you could imagine if you had 4 people mowing the lawn or painting a house or doing some other type of work, you just add another person here, and then you can have variables in terms of the what's known in terms of the different rates. This was like the most extreme because we're not given any specific rates, just everything in terms of a variable, and then we're keying off of that to say the second person is twice as fast and the third person is 3 times as fast. But you can still work with it, and you just get a general answer here rather than a specific number. So we have a different puzzle here from the last few. It's a tennis tournament. It could be any type of tournament. And let's look at the conditions. We have 1,025 tennis players in a single elimination tournament. So you lose once and you're out. They pair up at random for each round. If the number of players before the round begins is odd, then one of them is chosen at random and they sit out the round. The winners of each round and the odd one who sat out, if there was an odd one for a given round, they play in the next round until finally there's only one winner, the champion of the tournament. And the question is, what is the total number of matches to be played all together in all of the rounds of the tournament? Okay, so if you want to try this, I suggest you pause because I'm going to come back on this same slide and explain the answer. Okay, I'm back. Hopefully you got it. It's a trick question, so I didn't see it initially either. It kind of, you get thrown off by this large number here, and you might start calculating, each round, and that, well, I guess you could eventually get to the answer, but it's kind of the hard way to do it. And the other thing that's a little bit complicated is it's not a power of 2. If it was a power of 2, you might have been tempted to just go through the analysis manually, but it's one more than a power of 2. We handle that by this having the odd person sit out. So we could have just as easily given you a number like 377, and the analysis would be the same. You'll see in a second when I explain the analysis. So as I say, it's a trick question, and the key is that each player only loses once and they're out of the tournament, and there's one winner. So there's basically 1,024 losers, one tournament for each one of those losses, and then the one person who doesn't lose wins that very last game, and so you need exactly 1,024 games in order to come out with a champion in this single elimination tournament. And if I told you, like I said, 377, the answer would be you would need 376 games in order to come up with the final winner. Now you might have a lot of the sitting out in the different rounds because of the odd number and not being a power of 2, but the analysis is the same. So the source here is from an interesting book. It has a lot of good puzzles in it. Excuse me. Some of them are more complex. They involve calculus. Some of them are not so complex like this one here. This is more of a trick question. But if you're interested in puzzles, you may want to look into getting a copy of this book here from Paul Halmos, who's a famous mathematician. He's since passed on, but he's fairly well known in the mathematical circles, and he's written quite a few elementary books which are accessible by a lot of folks who just have a moderate amount of mathematical background. Okay, so let's move on to the next puzzle. We have an evaporation problem here, which involves a little bit of algebra. The hard part is translating from the words to an equation, which we'll do on the solution in the next slide. So we have a collection of watermelons, which are 99% water by weight, and by implication, there's 1% non-water, some other material. We don't care what it is, it's just not water. If 500 pounds of these watermelons are allowed to stand overnight, and if the partially evaporated watermelons are 98% water, so in other words, overnight the water percentage is going down from 99% to 98%, how much is their weight in the morning? So we want to know the weight of the what was 500 pounds of watermelon. What's the total weight in the morning given the reduction in the amount of water? And we assume there's no evaporation in the non-water part of the watermelons. Okay, so if you want to try that, pause here, and then I'll come back on the next slide and give you the solution. I copied the problem statement from the previous slide, so that's this paragraph up here, just so we had something to look at. So let's analyze the starting weights. 99% of 500 pounds is 495 pounds. So we start with that much water from the watermelons, and then of course what's left is 5 pounds of non-water. And we're told there's no evaporation in the non-water part of the watermelon. So in the morning, we're being asked if there's if the watermelons are 98% water after some evaporation in the morning, we're being asked what is the total weight of the watermelons, both the water and the non-water part. So we'll call that X. However, we know that the non-water part hasn't evaporated. So in other words, 2%, the 98 from the 100%, 2% of the total amount is still the 5 pounds that we started with. That didn't evaporate. And then we just divide the 0.02 on the 5 and we get 250. So a bit of a surprising solution. Even though the watermelons only had this small amount of evaporation, they went from 99% water to 98. The watermelons in total only weigh 250 pounds. So that's something to scratch your head a little bit. You want to think through this and reevaluate the conditions here of the puzzle, but this is the correct answer. I have a few age puzzles. These are things that you may have seen in high school algebra. Let's look at the first one. A mother is 30 years older than her son. So that's at present time. And 1 year ago, she was 4 times as old as her son. Find the present ages of the mother and her son. So you may want to pause here for a bit, and I'll come back and give you the solution on this slide. Okay, I'm back. So we'll let X be the mother's age and Y be her son's age. And we're told at present the mother is 30 years older than her son. So that gives us this equation here. The second condition is a little bit harder to write down. So it's saying 1 year ago, she was 4 times as old as her son. So we have to subtract 1 from the mother's age, and that equals 4 times her son's age, again, a year ago. So we have to subtract 1 from that. And then we can just solve this equation here. It's pretty easy. Just multiply to 4 times y minus 1. We get a 4y minus 4. Then we add the 1 there. So we get x equals 4y minus 3. And now we have 2 equations and 2 unknowns. And we have x equals something here and here. So we can just set these equal, which is what I've done here. So if y plus 30 equals 4y minus 3, we add the 3 to this side, we subtract the y here, we get 3y equals 33. So y is 11, and then that would mean that X, the mother, is 11 plus 30, so she's 41. So let's see if that makes sense here. If the mother is 30 years older than her son at present, yep, so she's 41 is 30 bigger than 11. And then a year ago, she would be 40, and he would have been 10, and so she would have been 4 times her son's age. So this checks out. The second age puzzle is a bit harder. We're just given ratios and not particulars in terms of their ages. The ages of Abe and Alice are in a ratio of 5 to 7. 4 years from now, the ratio of their ages will be 3 to 4. Find the present ages of each. So I'm going to pause here for a second and come back, give you a chance to work on this, and then I'll give you the answer on this slide. Okay, I'm back. So let the current age of Abe be 5x, and the current age of Alice be 7x. So that would give us our 5 to 7 ratio. And I know this is a little tricky here of why we didn't just call it x and y, but we're given a ratio, so we want to just keep it without adding another variable. We don't need that. In fact, it'll just confuse the problem. And then 4 years from now, so we add 4 to this, 5x, and 4 to the 7x, and then the ratio is 3 to 4. So we get this equation here, but again, it only has the one variable x, so we can multiply 4 times both sides here, and it'll cancel on this side, and we get 20x plus 16, and then the 3 on both, the 7x plus 4 on both sides. It'll cancel on this side, and we'll get 21x plus 12. Then it's pretty easy from here. You just subtract the 20x from the 21, and we get x, and then the 12 from the 16, and we get 4. And I'll leave it as an exercise for you to go back and check that the ratios are 5 to 7 and 3 to 4, just by plugging in x into these things here. That's fairly easy to check, but that's a good way of making sure you've gotten the problem correctly solved. We have yet another age puzzle. John's father is 4 times as old as John. That's at present. These puzzles usually work this way. If you're not told it's in the future or the past, you can assume it's the present. So this sentence here applies to the present. Then here we have something in the future. After 5 years, his father will be 3 times as old as John will be then. Find their present ages. So again, I'll pause and come back, give you a chance to work on this, and then I'll give you the solution. Okay, I'm back. So let x be John's age and y be his father's age. So the father presently is 4 times John's age, so that's y equals 4x. In 5 years, so we add 5 to the father's age, and he'll be 3 times as old as John will be then, so we have to add 5 years to John's age and 3, since we're told it's 3 times. We can solve this for y in terms of x. It's just 3x plus 15, but then we have to subtract the 5 on both sides, so we get y equals 3x plus 10, and then we can just equate these two equations for y, and we get 4x equals 3x plus 10, and you could almost solve this in your head. It's x equals 10, you put that back into either one of these, and you get y is 40. I have a couple more age puzzles for you to try. After your experience with the first 3, hopefully you'll be able to get these. They're a little bit harder than the ones we've seen. Not too much harder, but a little bit more. The algebra gets a little bit involved because you have to eliminate some variables from multiple equations. So let's just look at these. quickly. Frank is twice as old as his brother Eric. Eric is 8 years older than his cousin Rachel. In 5 years, Frank will be 3 times as old as Rachel. What are the present ages of the three? So I'll give you the answer on the very last slide of this presentation, and I'll use the variables f, e, and r. So you just see the answer in terms of f equals a given age, and e equals a given age, and r equals a given age. Then the second one is Abe has 2 children, Betty and Carl, and I'll use the variables a, b, and c when I give you the answer on the last slide. Carl is 3 years older than his sister. In 1 year, Abe will be 6 times as old as Betty is now. In 10 years, Abe will be 14 years older than the combined ages of his children at that time. What is Abe's present age? And in doing it, you're going to find Betty and Carl's age too. So I could have asked you for that too. So again, I'll give you the answers on the last slide. I won't give you the equations or the details of the solution. I'll give you the answers so you can check your answers. Okay, so give this a try. As I say, they're a little bit harder than the ones you've seen before, mainly because the algebra involves multiple equations where you need to eliminate one of the variables and plug that into another equation in order to solve the problem. The last puzzle in this lesson is called the coconut distribution puzzle. It actually is fairly well known. There's a Wikipedia page just dedicated to this puzzle. I've listed it down here. Let's talk about the puzzle and what are the parameters of it. So there's 5 men who've collected a pile of coconuts, and in the evening they decided that they would all get a good night's sleep and they would divide up the coconuts the next morning equally, 5 ways. But each of the 5 men kind of broke the agreement during the night. They secretly got up and took some of the coconuts, which I'm going to explain here what exactly happened. So the first man wakes up and the other 4 don't hear him, and he goes to the pile. He divides it into 5 smaller piles. And there's 1 additional coconut which he gives to a monkey, and he takes 1/5 of what's left after he gave the 1 coconut to the monkey. And then he puts all the coconuts back into a single pile, hoping no one's noticed. And the second man later wakes up. Again, no one knows that he's doing this, and he does the same thing. He divides the pile into 5. There's 1 left over, and he gives that to a monkey. He takes his 1/5. He puts all the coconuts back together again in a big pile, and he goes back to sleep. And then the 3rd, 4th, and 5th man does the same thing. So in the morning, there's still coconuts left, and it's actually evenly divisible by 5. So they're able to break up whatever's left in the morning into 5 groups of coconuts, and they each take whatever is left. So the puzzle is, given these clues, determine how many coconuts were in the original pile. And I'll give you a couple of clues. One is the thing about the divisibility at each stage, where you have 1 left over. That's important in order to figure things out. The other thing is there's no unique answer. There's a minimum number of coconuts you need in order for this process to happen, and so that's kind of what you're really being asked, is to find the minimum number. But there's actually an infinite number of solutions that get larger and larger. So it's not easy. Take a look at it, and I'll explain it in the next couple of slides. Let's look at a solution to our coconut distribution puzzle. We'll let x be the initial number of coconuts, and we want to determine what the minimum value for x is. So I mentioned on the previous slide, there's actually an infinite number of solutions, and I'll talk about that on the next slide also. So the first man looks at he gets up secretly, as we discussed, and he looks at the big pile, and he breaks it into, or at least he attempts to break it into 5 equal piles, but he has one coconut left over, which he gives to the monkey. So the 5 piles that he divides the large pile of coconuts into is each one is of size x minus 1 over 5. And as we're told in the directions to the puzzle, he takes one of these and then he leaves 4/5 x minus 1 coconuts. So what we started out as x is now 4 times x minus 1 over 5 coconuts. This is how many coconuts the second man is going to see when he does the same process. And for the purposes of calculations, I want to write this in this form here. If you multiply these both out, you'll see that you get the same number. It's not immediately obvious, but these will give you the same value. So we want to use this for our calculations. Let's just call it x prime. So x prime is what the second man sees when he gets up in terms of the number of coconuts. So he'll do the same process again, except he's starting with x prime. And so basically he'll end up with 4/5 x prime plus 4 minus 4, which is what I've written here. But we know what x prime is. It's this number here. So we just plug this in for x prime, as I've shown here. You notice the minus 4 and the plus 4 cancel. And then you get 4/5 times 4/5. You get 1625 times x plus 4 minus 4. And then you can call this x double prime if you like. And you plug that back into this formula here. And you would get 64 over 125 times x plus 4 minus 4. And then you do it again. And you do it one more time. So this is what's this is the number of coconuts that are left after the fifth man has gotten up, done the same procedure of dividing up what was left by the fourth man into 5 piles, with one left over, which he gives to the monkey. So this is what's left in the morning for the final distribution amongst the 5 men. So we have a little bit more analysis to do here to get our final solution, but we're almost there. So let's finish this off on the next slide. Let's finish off the puzzle. So just as a recount, we started with x coconuts, and we had this process where each man would wake up during the night, and first one, for example, would get up, take the coconuts, divide them into 5 piles, notice that there was one left over, give that to the monkey, and then out of the 5 equal piles, he would take one of the piles for himself, and then regroup the other 4 piles, and then the next guy would get up and do the same thing. So the pile of coconuts gets smaller and smaller throughout the night, and we figured out that at the end, after the fifth man had done this process, we have this equation for the number of coconuts that are left as a function of x. Now we want to find out what x is, and the first thing to notice is 3120. This has to be an integer, I guess I should say that first. So this number here has to be an integer, which means that 3125 needs to divide 1024, or x plus 4 exactly, and these two numbers are relatively prime. 1024 is a power of 2, and 3125 is an odd number, so they have no common factors, which means 3125 must divide x plus 4, and the smallest case, or the simplest case, is where this divides 3125 exactly divides x plus 4 one time. And we'll take that as our smallest answer. In fact, that is the smallest answer. And so x plus 4 would equal 3125, or we could solve for x and get 3121. So the smallest solution to the problem is to have 3,121 coconuts to start out with. We can plug this back into our equation for how many coconuts are left in the morning, and we get 1020, and in fact that is divisible by 5. It's pretty easy to see here, it ends in a 0. So that satisfies the final requirement of the problem. So that's our answer, 3121, but again, as I mentioned a few times, there's an infinite number of solutions, and we can figure out what they are. Surprisingly, or maybe unexpectedly, I should say, it's not any possible divisors in the x plus 4. In other words, we did 3125 dividing x plus 4 once, but it turns out if you assume it divides it twice or 3 times or 4 times or 5 times, it won't work out to get a pile that's evenly divisible by 5 at the end. So I checked different solutions, and it turns out the multiples of 3125, in other words, x plus 4 equaling some number times 3125, it only works for 1, 6, 11, 16, 21, 26. Basically, keep adding 5 to this number here. And I give one example. If you take x plus 4 equals 6 times 3125, then you'll have 6140 coconuts at the end of the process, and that is divisible by 5, which is the final requirement that we needed to have. If you try for, say, 5 times, x plus 4 equals 5 times this number, then it'll give you a number that's not divisible by 5. So we have to exclude those. But in final analysis, you still get an infinite number of solutions. It's just that it's these given multiples of 3125 equal to x plus 4. And of course, you have to subtract the 4 from it to get your value of x, and that gives you your infinite number of solutions. Okay, so that was the last puzzle in this lesson. I'll have a few more coming after this, so stay tuned.